Hi, I'm Adam.
Hi, my name is Hl1.
Hi, my name is Azhar.
Hi, my name is Mariam.
Hi, my name is Mariam Jamila.
And this is our video assignment for FAD 1007.
Doctor, my hand is itchy. I'm worried if it's getting worse on worse. Can you please check it for me, doctor?
Alright, let me check first. Okay, based on the report, you only suffers from minor rash. I will prescribe some medication for you, and I also recommend you to consume vitamin C to help your skin to heal faster by increasing the collagen production and also reduce the dark spot.
Alright, now let us take a look on the ascorbic acid structure. So the first thing first, we have to determine how much chiral center does it have. So as we can see over here, this is the first chiral center and this is the second one. So based on the chirality, we cannot just simplify say that this ascorbic acid is a chiral compound, as it has more than one chiral center. So it can be either chiral compound or maybe an achiral compound. So what we have to do is we have to find out if it has any plane of symmetry. However, as we can see, there is no plane of symmetry on this compound. So we can conclude that this compound is actually a chiral compound. Stereoisomer. So the first thing here we have in which the first stereoisomer, which is the ascorbic acid structure itself, in which the hydroxyl group and the hydrogen atom is on the same side, which is on the wedge side. So when we put a plane here, it will produce a non-superposable mirror image, which is this is the second stereoisomer. So the relationship between these two is actually the enantiomer. So this is the third stereoisomer, whereas the hydroxyl group and the hydrogen atom is on the opposite direction, in which the hydroxyl group is on the wedge side while the hydrogen atom on the shaded region. So when we place a plane here, it will produce a non-superposable mirror image, in which indicate the fourth stereoisomer. So the relationship between these two is the enantiomer. So the relationship between these two and this one is the diastereomer. So based on the naming, the first stereoisomer and its mirror image, it will become the L-ascorbic acid and the D-ascorbic acid. While for the third stereoisomer and its superposable mirror image with the fourth stereoisomer will become D-isoascorbic acid and L-isoascorbic acid.
Ascorbic acid has two pKa values because it has two functional groups, an indiol and carbonyl group. Since each functional group has its own ionizing pH, there is a pKa value for each protonation, which are at pH 4.17 and 11.6. Therefore, it is known as a diprotic acid, an acid that ionizes in water to produce 2 moles of H+ ion.
To form a basic salt, we would react a weak acid with a strong base in a neutralization reaction. By using ascorbic acid as our weak acid, we can use sodium hydroxide as our strong base for this reaction. Using 50 ml 0.5 mol of ascorbic acid and 50 ml 0.5 mol of sodium hydroxide, it would give us water and sodium ascorbate as the product. And this sodium ascorbate is the basic salt we are looking for. Since ascorbic acid is a weak acid, the equivalence point will be above pH 7 due to hydrolysis of ascorbate that increases the pH.
When we dissolve vitamin C in hot water, there is a lot of fizzles and many gas bubbles is formed. This is because the white tablets contain sodium bicarbonate, which will break down in water to form sodium ion and bicarbonate ion. The bicarbonate ion will then react with hydrogen ion to form carbon dioxide and water. The loud and vigorous reaction is because the hot water provides high energy for the reaction. So more collision between ions occurs in the medium. Due to the high temperature of the water, the proteins of the vitamin C are denatured and the nutrient content of the vitamin is reduced. So there is less nutrient obtained when we drink vitamin C in hot water.
When the vitamin C is dissolved in cold water, only some bubbles are seen and a very soft fizzle is heard. This is because the cold water has low kinetic energy, thus the reaction occurs at a slower rate than at room temperature water. In cold water, the nutrients are only inactive for a while until the temperature returns to its optimum temperature, so the nutrient content is still maintained in the solution.